In January 2026, astronomers announced they had found evidence of biological life on an exoplanet 124 light-years away. The compound they detected was dimethyl sulfide, a gas created by bacteria and ocean life here on Earth. Seaweed decays and releases it. Microbes in the water produce it. It's what gives rotting kelp its distinctive smell. The announcement raced across news networks and scientific journals. This was it. Humanity's first solid evidence of extraterrestrial life. By the time spring arrived, the biosignature had evaporated. Not because the gas disappeared from the distant planet, but because other researchers showed that the detection was far less certain than the original team claimed. The signal was weak and ambiguous. Multiple chemical models could explain the same data equally well, and none of them required life at all. The life-bearing atmosphere turned out to be just another planet with complicated chemistry. And so one of 2026's most striking announcements collapsed under the weight of scrutiny. But the story of K2-18b does not end there. What happened next revealed something deeper about how we search for worlds like ours. K2-18b orbits a star roughly 124 light-years from Earth. It belongs to a class of planets called sub-Neptunes, worlds larger than Earth but smaller than Neptune. The planet sits firmly in the habitable zone of its star. That's the orbital region where liquid water could exist on a world's surface, where conditions might favor the chemistry of life. For several years running, the James Webb Space Telescope had been watching K2-18b's atmosphere, decomposing its light into wavelengths and reading off the gases that compose the planet's sky. No instrument had ever examined a world so distant with such precision. The breakthrough in observational power opened a door. If microbial life inhabited K2-18b, its biological activity might leave traces in the atmospheric chemistry. Those traces might be readable by JWST. In early 2026, Madhusudan and colleagues published their findings. They reported a detection at 3 sigma, a statistical threshold that indicates reasonable confidence of dimethyl sulfide in K2-18b's atmosphere. On Earth, this compound is overwhelmingly biological. It comes almost entirely from living organisms. Seabirds produce it. Phytoplankton in the oceans release it. Methane swirled in the same atmospheric layers. Alongside other biosignature gases, the combination pointed toward life. Or so it seemed. Media coverage was swift and breathless. Some reports described it as humanity's strongest evidence for alien life. Then the scrutiny began. Other research teams took the same JWST data and ran it through different chemical models. What they found shifted the picture entirely. The signal was modest, ambiguous. The spectral fingerprint that Madhusudan's group identified as dimethyl sulfide could equally well result from abiotic chemistry, chemical reactions that require no life. Hydrogen sulfide, other sulfur compounds, different atmospheric layers with different compositions. All could explain what JWST had observed. You do not need biology to generate the light signature the telescope detected. By April, the biosignature claim had receded into the background of the literature. This is not a failure of the original researchers. Science moves by hypothesis and test. The hypothesis was plausible. The test seemed to support it. Further testing revealed the evidence was weaker than first thought. The planet remains interesting, but for now, it does not harbor proof of life. Yet the K2-18b system had more to reveal. If we cannot read life written in atmospheric gases, perhaps we can detect technology broadcasting from the planet's surface. In February 2026, astronomers conducted one of the broadest technosignature searches ever mounted. They aimed 2 radio observatories at the K2-18 system, the Very Large Array in New Mexico and the MeerKAT array in South Africa. These are among Earth's most sensitive radio instruments. They observed continuously for 33 days, precisely 1 orbital year for K2-18b, the time the planet requires to complete 1 circuit around its star. They monitored radio frequencies from 544 megahertz up to 9.8 gigahertz, a range spanning much of the radio spectrum where an advanced civilization might broadcast signals. The analysis was enormous. The instruments recorded millions of signals. Most were human interference, satellite transmissions, military radar, cellular networks. The team filtered those out methodically. What remained was the cosmic static, natural radio emission from distant stars, nebulae, and the diffuse medium of interstellar space. Buried in that noise, or absent from it, would be any narrowband radio transmission from K2-18b. They found nothing, no detectable broadcasts, no narrowband signals, no signatures of an alien technology. The null result carries weight because of the instruments involved. The VLA and MeerKAT are among Earth's most sensitive radio instruments. Their combined sensitivity set a new boundary. If a civilization on K2-18b was transmitting at power levels comparable to human broadcast technology, the observatories would have picked it up. The search did not prove that K2-18b is lifeless. It demonstrated what we can rule out, and with what precision. The astronomers framed their work not as final proof, but as methodological demonstration. This is how we conduct the search. These are the frequencies we can monitor. This is the sensitivity we have achieved. This is what we cannot detect with our current tools. The framework they built may guide future SETI efforts, the search for extraterrestrial intelligence, as astronomers survey other promising worlds. Each negative result teaches us something about how to search better. Meanwhile, JWST continues its atmospheric characterization of K2-18b. The same telescope that seemed to show a biosignature is still gathering spectra. Slowly, the planet's chemistry is coming into focus. K2-18b is not a second Earth. Its atmosphere is thick and hydrogen-rich, fundamentally alien. But that strangeness does not eliminate the possibility of life. It means that any life on K2-18b would operate under physics and chemistry radically different from what we experience here. The year 2026 began with hope. The hope of finding a biosignature, and moved into uncertainty. We did not confirm biological life. We did not detect technology. But we did advance our methods. We learned what we can measure and what we cannot. K2-18b keeps its secrets, but now we know the limits of the questions we can ask.